G6 limited edition vacuum cleaner.
What you see here is the CAD model of our system. Our system is a vacuum cleaner, and today we will be dissecting it. First, let's look at the entrance. You can see that the area is pretty large, and then the fluid will travel towards the impeller, which is this hole right here. What you'll notice is that the area decreases a lot, and we know from the mass flow rate equation that when area decreases, the velocity of the fluid increases. This hole in the back will lead into the impeller, which I'll show you right now. You can open the top, and when it gets inside the impeller, we can see the impeller blades. These impeller blades will catch the fluid that enters in the middle of the pump. You can see that the blades are kind of bent in a non-intuitive manner. You would expect them to bend in the opposite direction, but because the fluid increases the velocity as it moves radially outwards, the blade is actually relative to the fluid in a correct position, and they will catch the fluid as it moves outward. As the fluid moves from the center of the pump to the outer edge, its pressure increases and its velocity also increases. This might not be so intuitive because due to Bernoulli's principle, we would assume that as pressure increases, velocity would decrease. However, we must remember the fluid is not moving in a single streamline. Once this fluid gets to the edge of the pump, it will have high velocity and high pressure, and then it leaves the pump at the exit on the left side.
Section 9.6 talks about the ideal design of a centrifugal pump and states that the ideal design consists of an Archimedean spiral. An Archimedean spiral has the spacing between the impeller and the diffuser increase linearly as a function of angle. We can see in this image of the centrifugal pump that it matches an Archimedean spiral, and plotting the distance as a function of angle, there's a clear linear trend showing that this was designed as an Archimedean spiral. Chapter 9.6 also talks about the design of the impeller and states that we should find between 2 and 10 impeller blades and an angle of 22 to 32 degrees. We found a blade angle of 25 degrees and 11 blades. An increased number of blades reduces the load on each individual blade, reducing stress and the likelihood of fatigue failure, and increasing the lifespan of the vacuum.
How can we quantify the turbo pump? Well, we began by physically measuring a number of characteristics on the pump itself, which can be seen in this image. In addition, we then found the volumetric flow from a YouTube video and the power online. Using that, we were able to calculate the pressure based on the dimensions of our pump. The pressure gained, that, assuming air, was 482.4 pascals. This changes depending on the density of our fluid. However, using that pressure gain, we can calculate the specific speed and specific diameter, which are the same regardless of the density of our fluid. We got those to be 0.9855 and 2.167 respectively. The specific speed number lined up with our expectations for a centripetal pump. However, our specific diameter number was slightly lower than what we expected, indicating a mixed axial radial pump. However, this was still within the correct magnitude, so we are happy about that. We also calculated a head gain of 40.14 meters and a capacity coefficient of 0.0997 meters. Some density-based results were an efficiency of 4.1%, a head coefficient of 0.219, and a power coefficient of 198.5 for air.
Let's take a look at the hydraulic cover charts and the efficiency of our pump. Our calculated head value is around 130 feet, and our calculated flow rate is around 846 gallons per minute. Using the charts from the Griswold Pump Company, we see that our efficiency should be around 60%. Now we'll see that the horsepower in this is around between 40 and 50 horsepower, which is not accurate when compared to the specs of our pump, which means that this may not be the best measure of our efficiency, but it does give us some baseline.
Now that we determined our expected efficiency of our system, we can determine a theoretical percent that air and debris will be for a vacuum cleaner. Using that 60% efficiency number that we calculate from the pump efficiency curve and the hydraulic cover chart, and a expected debris for the vacuum cleaner to pick up to be 750 kilograms per meter cube, we can calculate an efficiency of that to be 2,540.8%, which is impossible. However, this indicates that the vacuum cleaner can pick up 2.3% of debris at a time, which makes sense because the bristles in the vacuum cleaner make sure that a large amount of air is coming into the pump at a time, and it's not just debris.
Let's discuss the viscous losses in the vacuum system. We experience essentially no viscous losses since our pipe length is just about 0.02 meters and the diameter is 0.05 meters. And assuming turbulent airflow, we know that the viscous dissipation factor is 0.0122. Using these values, we can calculate the viscous losses in pressure and total head. Calculations show that the viscous losses in pressure should be around 2.15 pascals and the losses in total head should be around 0.1791. These values do seem reasonable as the length of the pipe is essentially insignificant and should cause minimal viscous losses.